So I'm talking about the SPDF sublevel. And the SPDF sublevels have different numbers of orbitals. The orbitals are the dashes you draw in the orbital diagram. So the S sublevel has how many orbitals? 1. So anytime you need to draw an S orbital, you just draw 1 orbital, because how many electrons are in the S block across? There's 2. So going back to that, how many electrons are in each orbital? 2. So for every 2 electrons, you need 1 orbital. That's why in S block, since there's only 2 electrons across, you only need 1 orbital to allow for that to be filled. For P, so this is 1 orbital. For P block, how many electrons across is it? 6, because you go from boron to neon, there's 6 electrons across. So there's 6 electrons across, 2 electrons per orbital. How many orbitals do you need? 3. So that's why in the P's on the orbital diagrams, you go 1, 2, 3. And then you go, okay, this is like 2p or something like that. So the reason why is because you put 2 electrons in each orbital for a total of 6 electrons in that orbital. So that's why this makes, if you understand the electron configurations, then you can easily say, okay, I know how many orbitals I need to write so that I can fill up according to the electron configuration. So how many then would D have? How many orbitals? 5 orbitals. And then how many orbitals for F? 7 orbitals. And so it goes from 1 orbital to 3 orbitals to 5 orbitals to 7 orbitals. So it goes up by 2 each time. And that's because we said there's 2 electrons in S block. How many electrons in P block? How many electrons in P block? 6 electrons in P block. How many electrons in D block? 10 electrons in D block. How many electrons in F block? 14. So 14 divided by 2 is 7. 10 divided by 2 is 5. 6 divided by 2 is 3. So that makes sense if you know how the electrons are filling up. So on number 1, did we have any questions on that one after I kind of explained that? Speak now for ever hold your peace. Were you okay with that one then? How about this one, number 2? Yeah. Okay, so I explained this to some people to say just like fill up the 3rd energy level, but a lot of times we equate energy level to period. So like looking on the periodic table, hydrogen, and I like pointing at this one because this one doesn't show up very well with this red, I don't think so. So over there, hydrogen and helium are in the 1st period, but also the 1st energy level. In the 2nd period, we have all these guys, right? This is the 2nd period, also known as the 2nd energy level. But when you go to the 3rd energy level, you have a little trick here, because this is the 3rd period with sodium and magnesium, and all the way across. Sorry, my hands are shaking all the way across there. So that's the 3rd period, and also the 3rd energy level. But when you get down to D block, don't forget you do N-1. So this 3D right here, that is the 3rd energy level, even though it's in the, quote, 4th period. So to fill up the 3rd energy level, you have to go 3s2, 3p6, and then totally full would be 3d10. So some of you guys probably chose argon, which is a close call, because it is technically almost all the way full, but you can't forget that D is 3 does have a D block accessibility, so that you would need to fill it all the way up to zinc. So zinc is going to be including that 3d10 that you would need to fill all the way up to include the 3rd energy level. And then D contains 5 electrons in the S and P sublevel. How many electrons can S hold? You just told me. 2 electrons. So 4s2 is what you would write. And then if you have 5 electrons to work with, how many more do you need in P block? 3 more, because 5 minus 2 is 3, so you need 3 more right here. So you're looking for whatever element is that 4s2, 4p3. So 4p3, glasses on here. 4p3. So 4, this is 4s2, blah, 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 blah. 4p3 would be arsenic. Any more on this one? Identification ones. Logan? Yeah? Oh, yours is here. Okay. Yeah. C contains 1 electron in the 5s sublevel. So find 5s. So you go 1, 2, 3, 4, 5. There we go. 5s would be rubidium and strontium, but there's only 1 electron in there, so we're talking about rubidium because it's the first one. Any more? How about the rest of these that were related to drawing or doing your ions or anything like that? How about any others on Pump Set 5? Yeah, Lanisha. Excited state. Okay. So we only did one example yesterday, so I want to do another one. Let's do calcium. So calcium, just general old calcium. You have 1s2, 2s2, 2p6, 3s2. Is that it? No. 3p6, 4s2. That's general calcium, right? And if you counted, you see 20 electrons. You see atomic number 20, right, for calcium? Okay, so that's normal calcium. Its final shell is the 4th energy level, S block. So to excite that, it means that you need to cause its valence electrons to jump up to a future energy level, one that could be there, but it's not utilized because calcium only has 20 electrons. So you can shove one extra electron to a future energy level. And it can come in a couple ways. And I prefer to actually jump an entire energy level, but technically you can jump to a higher energy orbital too. And that's more kind of a different level of chemistry. But for calcium 2+, or calcium excited, I'm sorry, not calcium 2+, calcium excited state, I forgot I'm not doing ions, you're still going to have 20 electrons. You're not changing the number of electrons, you're just changing where they exist. So you're going to have 1s2, 2s2, 2p6, 3s2, 3p6, all the same. But when you get to this energy level, you need to change one of those electrons to a future one. So I'm going to keep one in the 4s, leave one there, and I'm going to make this extra electron to shift forward to an upper energy level, to 5s1. Noticing that, if you're looking at this and you read it, you go, oh man, she didn't fill up the 4s. What did she do? I didn't fill it up wrong. I excited the electron to make it jump to a future energy level. So if you count, there's still 20 electrons. So you know it's not an ion. You know it's just excited. That you could also write that as 4s1, 4p1, because technically the p's are of higher energy, but it's not higher energy level in itself. So I prefer this one, just because it makes more sense. Yeah.
Is this what you were talking about when you said it would look like an electron?
No. This one is definitely still calcium. It doesn't look like another one. It's just the excited state of itself. So when it falls back down, it creates light. But the one where it looks like another one is when it actually changes its number of electrons when it becomes a calcium ion. So this is calcium. This is excited calcium. Super happy, okay? And then we have calcium ion, which is literally lost 2 electrons. So the 2 electrons it would have lost would have been these two, because that's its valence shell. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, stop. Because who does this look like now? Calcium looks like, back it up to? Say again? Back it up, calcium backs up to potassium, then backs up to argon, thank you. So this electron configuration resembles argon because that's a stable electron configuration. And calcium ion, the only reason it's losing these 2 electrons is because it wants to be like the cool kids where it's been nice and stable. So these are 3 totally different things. Calcium normal, calcium excited, calcium ion. Yeah? 6 and 10? Okay, let me go over 10 first so I remember that one. 10, I'll go over quickly how to solve it, and I'm not going to all the way solve it. It was like 3.5 lines on the spectroscope. You had to do the spectroscope lab before you could do this question. The lines on the spectroscope, one line represented 1,000 angstroms. So how many angstroms is this? 3,500 angstroms. And then you were told in the lab on how to convert from angstroms to meters, where meters were 1 angstrom. No, let's go the other way. 1 meter was 1 times 10 to the 10th angstroms. So then you would convert 1 times 10 to the 10th angstroms to 1 meter, and then go from there. And that meter is gonna be wavelength, and then from wavelength, I think you had to find frequency. And then did you have to find energy?
Yeah.
Okay, so how would you get from wavelength to frequency?
Divided by.
Or what equation are you using?
This.
Right, speed of light formula, right? And then to go from frequency to energy, what would you do? Yeah, equals hv. So I think that's what you just need to go ahead and do. I'll explain 6 later though, because that's EMS stuff. Okay, any other random things? Randomness from set 5. We've been on this for like 3 days, so I'm trying to jump off from set 5 soon. Okay. So here's my game plan. We need to leave problems at 5 on your desk because I want to see your progress. And if it's 100, if it's 99% done, it's 100. Okay, I realize there's gonna be that one question you're like, I don't know. So ask me later, and I'll walk around for you guys who don't like asking questions out loud. We're not going to start notes just yet. So usually I like to have you do a quick introduction to what we're doing as a reading guide, right? And then the next day we talk about it. Well, I didn't assign reading guide 6 last time because I knew you guys were on that struggle bus with problem set 5. So reading guide 6 is something you're actually going to do tonight, okay? But I want to have you still introduce yourself to some of the concepts. But before we do that, I need to introduce you to one thing. So that's why you have this big worksheet on your desk, okay? So you'll get to this in just a second. So, oops, where am I at? I need to tell you about Coulomb's law before you're capable of looking into how introducing yourselves to this trends thing we're going to talk about, and then I'll let you guys work together, and then we'll come back together for notes. So here's me introducing Coulomb's law. Write down Coulomb's law first. And then if you didn't write down the valence electron stuff, we'll get to that shortly. Yeah, I am right now. Sure. Yep. This can be on the same sheet as the valence electrons. This can be the first part of your notes for today. I just need to explain how attractive forces work. I think most of us are good with attractive forces, but I want to tell you a little bit more information that's really helpful, especially for you like mathematically minded people. So write down this and I'll explain. I'm just trying to talk less and let you write more. I'm a talker. I don't know if you guys realize that. And people who are absent, I'm going to write down these things, or have you guys write down the absence as we go.
I had a question.
Is that number 10?
Uh,
On top step 5?
I also had a question on number 6.
Is that the photoelectric effect one?
No, it's the electron configuration of an atom of calcium in excited state.
We just remember, I'll go back to it. Okay. Okay, so when you're writing down the equation, you'll see that you have Q1 and Q2. Q1 and Q2 are just two charged pieces, two charged particles. Charges can be positive or negative. So in our case, right now, we're kind of mainly focusing on the atom. So the charge that we're talking about that's positive is a proton, and the charge that's negative is an electron. So protons live in the nucleus, electrons live in the electron cloud. If I have an atom that is, here's your nucleus in the middle, and your electron cloud's like yay big, their distance apart from each other is kind of small. Okay? If the distance is small, you could probably assume that that proton can really attract that electron quite well, because opposites attract for chemistry, right? So you can see that proton at the nucleus attracts electrons quite well. So it's going to have a tight hold on those electrons. And that's a qualitative kind of experience here. But if you look at it, it makes sense, because the smaller the distance, what happens to the force of attraction? You're right, it gets stronger because the smaller denominator makes the whatever it's equal to larger, right? So if you have 100 divided by 100, it's 1. But if you have 100 divided by 1, a small number, it's 100. So the smaller the distance between the two particles, or charges in this case, because Q means charge, the smaller the distance, the greater the force of attraction. So in this case, if we're talking about opposite charges, we're talking about forces of attraction. And I'm going to do the separate one in a different color here. Let's say I have an atom that is huge, and I have proton nucleus here, electron cloud. Woo! Okay, there. So electron cloud is there. It's huge. Here's the nucleus. I'm sorry. Here's the electron way out here. The nucleus is here. Their distance is quite large. What do you think is happening with the force of attraction?
It's
Much, much smaller, right? Because the larger the distance, which is the denominator, makes a smaller force of attraction. So pretty much that nucleus has very little hold on that electron. Do you think that electron can be lost very easily? Yeah, that electron is probably going to be donated to some other element who wants an electron. So as this atom loses that electron, is that going to form a cation or an anion? cat, right, because cat is positive, right? So it's going to form, losing electron means you're going to form a positive charge. So we're going to see how this works with something called periodic trends. But I just want to explain Coulomb's law to you because on the worksheet it says, explain this via Coulomb's law. This is Coulomb's law. Force of attraction is going to decrease or increase based on the distance from the charged particle. And I think it makes logical sense too. So, as an introduction, you're going to work with a partner, or three, I don't care, on how the periodic trends work. Periodic trends is just basically saying, across the periodic table or down the periodic table, does the atomic radius increase or decrease? Does the ability to take electrons increase or decrease? So we're just talking about the activity of the atoms. But there are trends, and a trend is like something that's generally true, and then sometimes there's exceptions, but it's still generally true. So you're going to do a little bit of the reading. You're going to try to make yourself get through 1, 2, 3 parts of the worksheet. We'll see. We'll say about 20 minutes. So if you have a good introduction, then hearing about it the second time when I talk about it is going to be much easier. Okay? So we didn't do reading guide since last night, so I wanted you to try this first. Okay? So for me, leave problem set 5 on your desk so I can see your progress. And then you guys can move around 20 minutes, get as far through this as possible. I have the periodic table because it's hard to see. I have it put up on the board for you too. Okay? So about 20 minutes. And you can write on a separate sheet of paper for this. And if you need to come scroll up here, then you can come scroll up here.